Okay, so last time we were talking about Gauss's divergence theorem. We talked about a bunch of applications to physics, and there's some pretty neat applications. One of them we talked about was electric fields, and reminder, electric fields can be thought of as a vector field. So, I mean, it's a pretty big physics concept, and it is a vector field. And several conclusions that you can draw as a consequence of the fact that the divergence is zero. It's amazing. Emphasis on away from where the charge is, right? So if you have a bunch of charge over here, that creates an electric field over here where there's no charge. Over here where there's no charge, the divergence is zero. Okay, so a bunch of conclusions that can be drawn. I went through the explanations for some of these, but not all of these. The big one that I want to end on is this right here, that the divergence of the electric field is proportional to charge density. Okay. Or, as you might say, flux density is proportional to charge density. Okay. All right. So we made a nice application of that there. But anyway, here it is again. Divergence of the electric field is proportional to charge density. I want to show you how this is part of a collection of ideas called Maxwell's equations. You've probably heard of Maxwell's equations. If you've had an E&M class, hopefully you've seen Maxwell's equations in some form or fashion. So I'm going to show you a neat fact about Maxwell's equations. And let's see here. So we're going to start. We're going to take these equations two at a time. By the way, there's a total of 4 of Maxwell's equations, depending on how you look at it. So we're going to look at the first 2. What I'm going to call the first 2 of Maxwell's equations, and these are they in from a certain point of view, and they're both about the divergence. One's about the divergence of the electric field, the other's about the divergence of a magnetic field. And I'm well aware of the fact that we haven't really spent any time talking about magnetism in this class, and we're going to say one little more thing about it a little bit later on, but not much. And I can't emphasize enough, this is not a physics class, and so we're going to kind of sideswipe the physics as to the extent that physics gives nice examples that helps us understand the math. Right, but the math is our focus here. Okay, so anyway, divergence of a magnetic field is 0, and not our problem as to why that's true. All right, we're just going to take that as a given. Okay, all right, so these 2 equations about divergence. Okay, so here they are again. Divergence of the electric field is proportional to charge density. There it is. You see right there. Divergence of the magnetic field is 0. There it is right there. And you'll notice all I've done down here in this next series of equations is take these 2 equations, do an integral, a volume integral on both sides of the equation, and then I'm going to cite the divergence theorem. The divergence theorem tells us that a triple integral of divergence is a flux. Right? Okay, well, yeah, but also, furthermore, a triple integral of a density gives you a total quantity. Right? So a triple integral of charge density gives you charge. A triple integral of, well, conveniently 0 gives you 0. So there's no work to be done there. Okay, so the big idea, though, is that most of what's happened here is we take these 2 theorems up here, take a triple integral of both sides, and then invoke the divergence theorem. And note that the punchline of these equations here is that flux, magnetic or electric. Let's just rewrite the equations like this. Flux, these equations that were about divergence are now equations about flux. Yeah. Okay. So what we have here is what you might call an alternate point of view on these original 2 of Maxwell's equations. These original 2 Maxwell's equations are about the electric field, specifically the divergence of the electric field. Down at the bottom, we have 2 equations. I should have said electric and magnetic field. Down here at the bottom, we have 2 equations also about electric and magnetic fields, but just about the flux of those fields. Okay. Okay. In fact, here, let me say now yet again a little bit differently. This equation here says flux density is proportional to charge density, and this equation down here says flux is proportional to charge. They say the same thing, just the ones at the top have the word density at the end. That's it. Right? So they're really, really very similar versions of the same equation, morally. Right? This said kind of in a local sense involving derivatives, and this in a kind of a global sense involving integrals. But they're about how flux relates to quantity in both cases, just one in a density sense and one in a cumulative sense. So even though these are different equations, they are thought of routinely as not so much two different equations, but two different versions of the same equation. So thus the lingo here. So these are referred to as the differential versions of these two of Maxwell's equations. And these two down here are referred to as the integral versions of the same equations. So this is kind of, again, depending on the point of view, viewed as two equations in two different forms instead of four equations. Okay, so anyway, you're going to see, if you take an E&M class here at Duke, and being engineers, I think a lot of y'all either have or will, there's going to be a bunch of discussion of Maxwell's equations, and I think it's very valuable to understand not only the two different points of view, the two different versions of each of Maxwell's equations, but why they're connected, why we consider them to be really kind of the same as opposed to totally different things. And again, the thing that makes that connection, why am I talking about this in a multivariable calculus class? This is not a physics class. It's because Gauss's divergence theorem is the thing that makes that work. Yeah.
So the equation of Rayleigh says magnetic flux equals 0. Does that mean that there's no such thing as magnetic flux, or it just always equates?
No, there certainly is such a thing. It's just that it's always 0. Yeah, it's kind of weird. So, if you have electric charges, right? Imagine some electric charges here. If you put a ball or a surface that encloses those electric charges, you're going to have a positive electric flux. What this is saying is, no matter what ball you put in the vicinity of a magnetic field, that magnetic field flux will always be 0. Another way of saying that is that there is no such thing as a magnetic charge that you can put inside of a surface and thus, expect to get magnetic flux. Sometimes they talk about magnetic monopoles. That's kind of what they're talking about. Okay, great question. Yeah. So you can certainly, this magnetic field, it's a field, you can take the flux of it just like any other field. It's just that, amazingly and weirdly, you will always get 0 as your answer. Yeah. Okay, so credit Gauss's divergence theorem. All right. Some of y'all have noticed already, and I kind of hinted at it previously, that the twist that we put on Green's theorem a while ago, right? We wrote down this idea of flux through the boundary of a curve, and we did a twist on an adaptation, I'm calling it here. We tweaked Green's theorem in a certain way, right? By relating normal vectors and tangent vectors. Well, they're just related by way of a 90-degree turn, and if you observe how the dot products do such and such, then you get this result. And so this originally came up as a twist on Green's theorem. So, and then I hinted that we would have an accumulation point of view on this result, later. And here we are. So let me show you how this works out. And it's really, it's just Gauss's divergence theorem again, just applied in a two-dimensional setting. And we're going to go through all of exactly the same ideas, right, and applied and appropriately in the context to get down to it. I'm going to skip all the details because it's so similar to what we did with the three-dimensional version. Okay, so if you have two-dimensional regions and their boundaries, now curves, of course, instead of surfaces, right? Three-dimensional regions have boundary surfaces. Two-dimensional regions have boundary curves. But in both cases, you can still talk about flux through that boundary. And so we have already talked about flux through a curve. If you have a curve, right, and a well-defined direction of which way you want to be thought of as the positive flux direction through that curve, then we wrote down formulas. Okay. All right. So observation. Flux accumulates. And it's just a matter of, drawing the picture. Here, let me zoom in a notch. Let's look at this region here, for example, D1. That region D1, right, if you look at its boundary includes C3, oriented the way I have indicated as the orientation of C3, and so as part of the boundary of D1, we get a positive C3. Right? And then, of course, also C1. All right. But thought of as part of the boundary of D2. Right? Here's D2. Thought of as part of the boundary of D2. We still get this curve, C3. That is part of the boundary of this green region. But it's as part of that boundary, it's oriented that way, which is not the direct. C3 I've arbitrarily designated. C3 is oriented to the right. So as part of the boundary of D2, I need to talk about negative C3. Right? Not positive C3. It's going the wrong way. And so, no surprise, here's that same cancellation that we've gotten in previous instances, right? We have a plus C3, we have a minus C3, they cancel, and yes, boundaries accumulate. The boundary of the whole is the sum of the boundaries of the individual pieces that you chop it up into. And so I've drawn the picture for two pieces, but you could imagine if you have a large number of pieces, again, every slice you make, each part of that slice is going to be part of the boundary of, the piece on one side and the piece on the other side. Same story. Repeated many times. Okay. All right. By the way, here's another way to think about that same thing. Imagine that we're thinking of flux. Flux relates to a flow of some sort of a fluid. So we're now in 2 dimensions. We don't typically think of fluids in 2 dimensions. We think of them in 3 dimensions, like the air in this room. There's a certain amount of this air is flowing around the room in certain ways. So imagine now that we're talking about on a surface, and so maybe there's a couple of different options. You could think about surface water and how does surface water flow on the surface of the earth, right? It's pretty much 2-dimensional. We can think about migration patterns of, whatever animals you're interested in. They pretty much, I suppose birds go up to some extent, but we don't really, that's not migrating, right? If they're flying straight up, or to whatever extent they're going up, who cares? Where they are is pretty much a function of what land are they sitting above, right? So effectively, a migration pattern is a flow of a fluid in 2 dimensions. Okay. And so the idea is, looking at this shared boundary curve here, hit that better than that. Looking at that shared boundary curve, if the fluid flow is like this, right, to whatever extent that represents a, wildebeest, right, leaving D1 by crossing that line, that exact same wildebeest is also entering D2. To whatever extent you have positive flux through that purple curve as part of the boundary of D1, you unavoidably have, again, perfect pairing, animal for animal, a negative flux for that piece of curve thought of as part of the boundary of D2. So they just have to cancel. So, okay. All right. Okay, so flux accumulates. Now let me. It's almost over, but there's flux accumulates. The total outward-oriented boundary flux, right, over the whole region, is the sum of the outward-oriented boundary fluxes over the little pieces. That's the accumulation feature we just talked about. Multiply and divide by area. Throw in a limit, because the limit of a constant is the same constant, therefore you can say limit for free. And lo and behold, again, notice the pattern. It's the same strategic pattern that we've taken in all these other theorems, and I have a double integral, right, of, well, now we got to figure out what this turns into. There is this question of, in the limit, what happens to outward-oriented boundary flux per unit area in a situation like this. And this is a calculation. It's details. And I'm just going to assert that in much the same way as it did for the three-dimensional version, this is what you end up with. It is, flux per unit area. Boundary curve flux per unit area. Yeah.
And is that also equal to Green's?
Well, this is identical to the adaptation that we made of Green's theorem. We took Green's theorem and kind of twisted it around in a certain way and derived this as a result. So this is reproducing that same result. It's therefore kind of, I suppose, technically kind of equivalent to Green's theorem, but Green's theorem we think of as a different sort of accumulation. Just as a reminder, we think of Green's theorem as an accumulation of circulation as opposed to flux, right? So, but it's equivalent to the twist that we did. Yeah. Does that answer your question? I'm not sure. Yeah. Okay. Yeah. Okay, so just different point of view. So again, henceforth, instead of, up before this morning, your point of view, the point of view that I gave you anyway on where does this theorem come from and how do you think of it was, this is a twist on the idea of how circulation accumulates. Right? And now I would like you to think of this in a different way. I would like you to think of this as a statement about how flux accumulates. It's not a twist. This is its own result. Right? It's arguably a lot more like a lot more like Gauss's theorem that we saw last time than it is about Green's theorem. So if you want to connect this to one of the other theorems, connect this to Gauss's theorem. Right? It's about flux. The resulting integrand is divergence. Right? It's cosmetically, practically a ripoff of divergence, of the divergence theorem. Okay. All right. Okay. Before I go on to Stokes' curl theorem is the next thing, I want to flip over to this other page. So this is on Sakai. I'm 95% sure I put this on Sakai. If I haven't, please remind me, and I will be sure to put this document on Sakai. It's just a little bit more notes. I want to talk about the accumulation, the sort of the relationship between various theorems we've talked about as pertains to accumulation, and more to the point, how you therefore interpret the resulting densities. Okay. All right, so here's a point of view of the fundamental theorem of calculus, and again, I know y'all understand the fundamental theorem of calculus. F of b minus f of a is the integral of f prime, right? All that business. Okay, so as you recall, we think of that as a way of measuring change. If you give me some interval, and if I were to say, okay, looking on the boundary, looking at here and here as 2 points, how would I compute the amount of change? What is f of b minus f of a computed on this, the boundary of this interval, namely the points a and b? So when you talk about change, you compute change on the boundary. It's a boundary computation. Okay, but it is perfectly obvious, right, that that's not where change happens. Of course not. Look at the function. Watch what the function is doing. The function is whoop like that, right? Where is the change happening? Is the change something that just magically happens on the boundary? No, come on, don't be silly. The change, this is where the change is happening. Look at what the curve does, right? That's where the actual change is going on. Yeah, everybody on board? Okay. Perfectly relatable, right? I mean, again, think about anything that changes in a continuous manner. The change happens, the change is measured at the endpoints, but it actually happens in the interior. Very literally. Okay. All right. So I want to point out that the same is, I'm sorry, I got ahead of myself. Not only does the change happen in the interior here, right, as you can see from the graph, but furthermore, the integrand, right, so we know that change is an integral of f prime, right? This integrand here, f prime, is a direct indicator of where that change is happening, right? There's a lot of change happening in this general vicinity of the domain, and you can see that by the fact that the slope, the derivative, right, the rise over the run, is large there. Change density, right? Okay. Whereas now, not as much change, maybe a little bit of change, but not as much as happening over in this general vicinity, because you look at the little triangle there, and the rise over the run is just smaller. So f prime. So not only does change happen in the interior, but the corresponding integrand, f prime in this case, is a direct indicator of how much change is happening in any given specific place. Okay, that's the name change density. Okay, so I want to go down here and let's talk about how does the same idea apply to. I want to start with Gauss's theorem here. All right, so now remember, we've got some original domain, and we talk about its boundary. Right, just like up here, we were talking about this interval. And then we looked at its boundary points, and we looked at a calculation that happened on that boundary. Here it was change. Here, on the boundary, we're not looking at change. Here we're looking at flux. Right? So, again, you look at the formula for flux. The flux through a surface is a formula that you write down that is computed directly on the surface. It's computed on the, in this context, a boundary. Okay. We compute it on the boundary, but that doesn't mean it's actually happening on the boundary. Come on, it's perfectly obvious. It's not actually happening on the boundary. It's just computed on the boundary. Where it's actually happening is in the interior. Just like this story here, the change is happening. You can see it happening, and it's happening in this part of the domain, in the interior, right? Likewise, you can look at the vector field, and even though, sure, we computed on the boundary, well, that doesn't mean it's happening on the boundary. It's actually happening in the interior. And now we're not trained yet to, exactly to look and see, and tell, where is flux actually happening. But I'm going to draw some pictures that try to persuade you that this is where that boundary flux that we measure is actually happening. Okay, so let's draw some pictures, and I'm going to go in a notch here. So let's see here. Let me draw a little rectangle here. There's a little rectangle. And remember, we know that the total boundary flux is the accumulation of all the little boundary fluxes in the interior. You take this region, you chop it up, right? A bunch of little pieces. Okay, so on that little piece, let's talk about outward-oriented boundary flux on that little piece. Okay, well, there's no flux happening. There's no flux happening on that edge. The vector field is going parallel to the edge, not perpendicular to the edge, so there's just no flux on that edge. Likewise, there's no flux on that edge either. Right? Okay, in fact, let me zoom in another notch or two here. Okay, but there is flux happening on that edge. And specifically, and I've got to get into eraser mode. Specifically, on this edge, you can look at the vector field. You've got, that strength of vector field being multiplied by that length of curve, and you can see that there's a certain amount of positive outward-oriented boundary flux happening on that edge. Okay, sure. Well, now, but what about on this edge? On that edge, the field is just as strong. The edge is just as long. You're going to get the same amount of flux, but it's inward instead of outward, and so grand total here, all edges considered, the outward-oriented boundary flux here you expect to be 0. And roughly speaking, we expect it to be 0 because there's just as much outward flux as there is inward flux, right? And I argue that Same is true here, same is true there, same is true there. Yeah? Okay. Now over here, the field lines are shorter. Uh-oh. Does that change anything? Well, no, they are shorter, yes, but they're, again, still, the same length on that edge as they are on that edge, and they cancel. And so there's no boundary flux happening there either. Okay, so where the flux is happening, where it's actually coming from, is where's my little thingy? Here it is over in here. And just think about the same little exercise. Now the field lines are still going that way, and so there's still no flux on that edge or on that edge, so we don't have to worry about those. On this edge, okay, well, there's a field line there that's going through, and the field lines are kind of long. Compared to over on this other side, the field lines are shorter. So yeah, you've got a positive boundary flux on that edge, and yeah, it's a negative boundary flux on that edge, but it's less negative and more positive. Everybody see that? Okay. So on this little region of the there we go. On this little region of the interior, that's where the flux is happening. You can see it, right? It's, oh my gosh, look at the, you can almost imagine this was a migration pattern, right? You'd be thinking to yourself, okay, well, there's this, the wildebeests are, as they move, well, along in here, there's a certain, here they go, look, there they go, there's wildebeests, right? But there's it's this constant pattern of wildebeests, and then, mysteriously, in this general area, a certain number of wildebeests go in, and then even more wildebeests come out. How'd that happen? Right? There is spontaneous generation of wildebeests over there. Somebody's airdropping wildebeests. Right? So that something is clearly happening in this general vicinity here. Right? And then, the increased forces of wildebeest along in here. Well, yeah, there's a lot of wildebeests walking in, and there's a lot of wildebeests walking out. So there's no airdropping of wildebeests. There's more wildebeests over here, but it's a consistent wildebeest in, wildebeest out. There's nothing really that interesting happening. This is where, again, we've got this, grand total around the entire edge. If you were to look at the entire edge, right? There are more wildebeests going out than there are going in. Somebody's making wildebeests. Right? Where are the wildebeests coming from? They're not coming from over here. There's just as many, that's just where wildebeests walk through. This is just where they walk through. This is where they're making wildebeests. Yeah?
Could it be that the wildebeests are just getting faster?
Yes, but I want to talk about it. That's a great question. In my scenario here, we're talking about a steady state pattern. So if they were getting faster, and you're right, they certainly could, then the the wildebeest population down in here would have to be going down at a rate, and so that's not steady state sustainable. Yeah, no, it's a great question. Absolutely. Yeah. Okay. All right. So I think the analogy is extremely strong. Let me go back up to here. Can't get the thing to erase. Here we go. So, sure, you measure accumulation on the boundary, but it's actually happening in the interior, and the indication, the local, specific computational indication that you can get of, how much in any given place? Well, the derivative. The integrand of our new theorem, right, tells you how much of this thing that you're measuring on the boundary is actually happening in a given specific place. Likewise here, the accumulation is measured on the boundary, right? But that does not mean that that's where it's actually happening. This is where that outward-oriented boundary flux that we measure is actually coming from. It's literally accumulating over the interior. specifically there. Right? So divergence is a way of measuring, to some extent, divergence is a way of measuring how much in a general vicinity, how much more of there's more sort of outward than there is inward. How much of this kind of thing is going on? And it can take different forms. It can look like, it can look like this, right? Or it can just look like this. Right, this is the classical sort of, oh wow, that's where the stuff is coming from kind of a picture, this emergence and, flow in all directions out of a single place. Right, so roughly speaking, that's what divergence looks like. Okay. All right. Last variation of this that I'm going to talk about, and then we'll go on to Stokes' theorem, is Green's theorem. And I'm going to be, quicker about this because it's same ideas. Okay. So Green's theorem is about a calculation. About a calculation that happens on the. Sorry, I tried to switch to the thing there. Okay. A calculation that happens on the boundary. It's not flux. Right? Green's theorem is about circulation. So, nevertheless, there's a certain amount of circulation that you can measure on that outward-oriented, on that counterclockwise-oriented boundary. Now, if you look at the vector field I have indicated here, there's no circulation there. The field is that way. The curve is that way. And the dot product is 0. That's not circulation. Okay. Oh, come on. I just wanted to delete. There we go. Okay. All right, and likewise, that's not circulation, right? So circulation is what's happening there. As I go in that direction along the curve, the field is also going in that direction, and so there's a positive circulation happening there, and analogously, a negative circulation that's happening there. And I think you can see that there's more positive than there is negative. Right? Longer field lines contributing to the positive, shorter field lines contributing to the negative. Okay. Right. So circulation, as measured on the boundary, is positive. Yes, question.
So circulation is like when the arrows move in the same direction as the boundary?
Yeah, so remember this point of view we have on circulation, well, in fact, on vector line integrals in general, is thinking of, interpreting the vector field as representing a fluid, right? Line integral, that's what a circulation really is. Line integral is a way of measuring to what extent is the fluid flowing along the curve. Right? And so here the fluid is flowing along the curve quite substantially. Here the fluid is flowing along the curve but in the wrong direction. Right? The curve is going to the left, the fluid's going to the right. So yeah, does that make sense? Yeah. Okay, so grand total, we've got some circulation. The circulation's measured on the boundary. Does that mean that's where the circulation's actually happening? No, of course not. We look at little regions. Let's look at a little tiny little box there. On that little box, well, obviously there's no circulation happening on these two edges. Right? There's positive circulation there. There's negative circulation there to the same amounts because the field's got the same magnitude. You're getting positive circulation there, negative circulation there, and the exact same amount because the fields have the same length. Okay, so and again, let me zoom for visual effect. So up here, right, looking at a circulation around that little box, you get 0. So all this circulation that we're measuring on the outside, that's not where it's coming from. The circulation happening here is 0. Ditto there. Ditto over there. Ditto up there. Ditto down here, ditto there. Now, there's more field happening here. There is more positive line integral on that edge and more negative line integral on that edge that are still canceling to give 0. So there's more flow, but there's still 0 circulation. Okay. All right. So again, where the circulation is happening is kind of up in this general vicinity. And let me go up to here. That's where circulation's happening. Here we have more positive circulation, less negative circulation, which adds up to positive circulation. Everybody on board? Okay, so that's what Green's operator measures. Green's operator measures to what extent is there, locally, per unit area. I mean, obviously, if you made this little rectangle really, really teensy-tiny small, you're going to get a very teensy-tiny amount of circulation because you're looking at really short little pieces of length. And the difference between the top field and the bottom field are going to be very small. And so smaller pieces, smaller circulations, of course. But in terms of per unit area, Green's operator is measuring how much this kind of thing is happening. Everybody on board? Okay. All right. Okay. By the way, there's a physical metaphor that I like. If you were to think of this field, with short lines, short vector arrows there, and longer vector arrows here like this, I like to think of this as the surface of a river. Right? And I don't know if you all are aware of this, but this is pretty relatable, I think. If you were on the bank of a river, that's blue is the river. What's the matter with me? If you were on the bank over here next to on the grass, the water flow is not very fast right next to the edge, but the water flow is quite a bit faster further in. Right? Okay. All right. So here's here's a physical way of thinking about what Green's operator measures. Imagine that you have a leaf, right? Right. Some let's say a nice dead leaf, so it's got little mass, very little, it's kind of rigid, right? And it's going to float. Let's think about what's happening to this leaf as the water hits it. The water is pushing it on that side, but the water is pushing it also on that side. And so, big surprise, the leaf's going to flow downstream. Of course it is, right? But it's being pushed on the top side and the bottom side about the same amount. And so you would expect it to, as it goes down the river, to just kind of go down the river like that. Does that make sense? Okay. On the other hand, let's suppose it was here. Right. Well, now it's being pushed on that side some, but it's being pushed on the other side more. And my program is not set up to make an animation for this, but as this river, as this leaf is pushed along down the river, not only, of course, it's going to go downstream, obviously, right? But as it goes, it's going to twist, right? And this is pretty observable. Throw something into a river where not too far away from the edge, where you can visibly see that the water is faster in this area and kind of slower in that area. Throw a stick maybe or whatever, right? And you will see that stick kind of twist as it goes down the river. So Green's operator could be thought of in a context like this as measuring how fast is the floating object going to twist as it goes down. Cool. All right. Okay, so back up to here. So new theorem, Stokes' curl theorem. So this is our last big theorem of chapter 15. Same ideas, different context. So I'm going to go again a little bit more quickly through the kind of the part of the development that's all the same, but there are some differences in how we apply this chop it up, add it up sort of density sort of accumulation and the density sort of strategy in this context. So first of all, what domains are we talking about? Well, we're talking about a domain and a boundary. Okay. The domain is going to be a surface in R3. All right, now reminder, we've talked about solids, right, with their boundary surfaces. That gave us Gauss's divergence theorem. We've talked about two-dimensional regions in R2 and their boundary curves. Sure. But we've never talked about a two-dimensional domain, namely a surface, in a three-dimensional context. Right, so this is kind of altogether a slightly different thing. So domains and their boundary curves. The domains are surfaces, and the boundaries are their boundary curves. And obviously, the boundary of a surface, right? If you have a surface, the boundary is a curve, some way or another. All right. Now, just like with Green's theorem, when we were talking about Green's theorem, we had to decide what we meant about, what's the correct direction to go around the boundary curve, and it's an arbitrary convention with Green's theorem that, given a region, you go around that outside edge. You always go what ends up being counterclockwise around the outside edge. Arbitrary convention. Somebody asked a great question. Why counterclockwise? And the answer is no good reason. Right? Ultimately, no good reason. But at this point, everyone, right, makes this same arbitrary convention. And so right now, the good reason to do it this way is because everybody, if you want to be able to effectively use the Green's theorem in discussion with anyone else, you got to do it this way. Okay, so. All right, so what is the correct direction to go around the boundary of a surface? And there's a temptation to say, how about counterclockwise? Seems reasonable, right? If you got a surface here, let's just go counterclockwise around that boundary. Awkwardly, though, what if your surface is vertical? Or what if you're not, from your perspective, you're looking at it kind of edge on. Counterclockwise as seen from that side, or counterclockwise as seen from that side, right? And back to this sort of more convenient surface, counterclockwise as seen from up here, or counterclockwise as seen from down here. They're not the same, right? So, which way is my finger rotating? Y'all think it's counterclockwise. I think it's clockwise. Right? So there's a nasty little problem. So counterclockwise doesn't even make sense in this context, right? So we have this nasty little question. If we're going to say the word boundary, and if we need to have an orientation, a standard conventional choice of which way is the right way around that boundary curve, we need something different. And here's the convention, and yes, completely arbitrary. But again, this is just how planet Earth does it, and so we kind of have to get on board with this arbitrary convention. Okay, and it's fine. Right? Who cares? Okay, so here's the rule. If you have a surface. Now, by the way, this is not just some surface. This is an oriented surface. So the surface has to come with an orientation. Arbitrarily, I'm going to say this one's oriented, what you might want to call up. Right? Let's just say. An oriented surface. Okay. How do I tell what the proper orientation is on the boundary curve? Here's the boundary curve. Right? Should I go, that way? Or should I go that way? And the answer is as follows. Take your normal vector. Orient your thumb of your right hand. Apologies. Right hand only. It's got to be your right hand. Really makes a difference, right? Thumb of your right hand in the direction of that normal vector. Notice that your fingers of your right hand want to bend a certain direction. So again, no hand yoga, right? So your fingers want to bend a certain direction. That defines what I'm going to loosely, let's not be uptight about this, loosely call a swirl on the surface around that normal vector. All right, is everybody on board? So now then think about that swirl. How does that swirl sideswipe up against the curve? That's the direction that you go around the boundary curve. Right, so now notice, in order to be able to get an answer to this question, you can't put the normal vector on the boundary. Don't go on the boundary, because we need to be able to have a swirl that goes around the boundary. If you're on the boundary, then it kind of hangs over the edge and the whole thing doesn't make any sense, right? So near the boundary, use your right hand, fingers make a swirl. That's the correct direction to go around the boundary curve. Everybody on board? Okay, yeah, please.
Can you explain again how you have like a 2D boundary and a 3D?
Oh, well, yeah, if you have a solid three-dimensional thing, right, like a rock, right, the boundary of the rock is like, if you were to get the rock wet, where's the water, right? It's and it's just a surface. It's a two-dimensional surface. Planet Earth, right, it's a three-dimensional thing, but we live on the surface. The surface is a two-dimensional. The boundary of where is the edge between Earth and not Earth, right? That's the surface of the Earth, and it's a surface. That kind of thing.
Isn't that kind of like what we did with Gauss's divergence theorem?
Yeah, but I'm sorry. I thought you were talking about Gauss's divergence theorem. So here, very importantly, we're not talking about a solid and its boundary surface. Here, we're talking about a surface and its boundary curve. Yeah, so it's a two-dimensional surface, right? And then its boundary is just what you might call the edge here, and that's a curve. That's a one-dimensional thing.
Well, like in that case, wouldn't it be like Green's?
Green's theorem happened in 2 dimensions. So this is the complication on this is that the surface might be bent, right? This is a much more complicated structure to try to deal with, because it could be bent and twisted around in space, and the boundary curve is not flat. The boundary curve is correspondingly sort of twisty. Yeah. So I mean, it's got a lot in common with Green's theorem, absolutely, but it's a different thing. Yeah. Yep.
What if the surface we're interested in as a sphere or something like that?
Yeah. Okay. Right. So a sphere basically has no boundary. Right. So there just isn't a boundary there. It's like a curve. Imagine you were going to do the fundamental theorem of calculus, right? You talk f of b minus f of a. Well, what if your curve starts and ends at the same point? Then it kind of doesn't really have a and b are the same point, and so f of b minus f of a is always going to be 0. So it's kind of like that. Right, so there effectively is no boundary, or you might say the boundary is 0. Okay, so this is the convention. By the way, there are variations of this. Some people like this other version, where you take the normal vector and you use the normal vector as a way to draw a little stick figure, right, whose head is at the head of the vector and whose feet are at the tail of the vector, and then you tell the little stick figure, okay, walk to the edge and then turn left, right, and that's fine, right, but here's the problem. Here's a surface with a normal vector, right, you can imagine a little stick figure guy, and he's walking over there and turning left, right? What if your surface is like this? Right, if your surface is oriented upside down, and then you're going to find yourself on the exam kind of like, okay, now I'm the stick figure man, and now I walk along, and then which way is left, and you can see it's really easy to get confused, right? Whereas, if your surface is oriented upside down, then thumb down, fingers, and I can sit upright very comfortably and look and just see which way do my fingers swirl, right? Yes?
If the surface is oriented upside down, can you just use your left hand?
Oh gosh, please don't. I'm sure there is a variation of the rules that will allow you to get right answers, and there's lots of different sort of points of views. But in order to avoid sort of endless trips into, oh gosh, yeah, I'm just going to say please don't. Right? So your right hand can point upside down. I mean, here's one thing you could do. You could say, let's look at the orientation, the downward orientation, right? And say, okay, I'm gonna insert a sign error by assuming that it's right side up oriented, and then I'm going to introduce another sign error by using my left hand. That is true, right? But keep in mind, the point of view in this class is not about whether you get the right answer. The point of view is about whether you use good ideas. And point of view could be taken that 2 sign errors is 2 errors, right? Even if they're canceling. So that I don't have to try to figure out who got lucky and made an even number of mistakes, right? As opposed to, who's just completely wrong, right? It just makes more sense to let's stick with the right hand, and it's kind of like with the backwards time thing, right? That's a point of view that gives you right answers, but it kind of doesn't really. It's unnecessarily contorted. Doesn't really make any sense. Yeah. So that's a very good question, but let's. I'm going to say let's not. Yeah. Okay. All right. So. On this context of surfaces and their boundary curves, we're going to be computing circulation, just like we did for Green's theorem, and I seem to be out of time. So I'm going to make the case next time that even though it's computed on the boundary, circulation accumulates over the interior, and we are going to get a new kind of boundary theorem. And we'll see that on, oh my gosh, today's Monday, holiday on Wednesday. So see y'all in a week. Have a good Thanksgiving, everybody.